Uh, thank you. Thank you first to the organizers for letting me talk today. So I'm François Lavoue, same as yesterday, but on a different topic today. Today I will speak about how we can use train signals for passive seismic imaging and monitoring. And this is a work that has been performed mostly in the Pacific project, which is now finished. And maybe you remember Florent last time, 3 years ago, who I think presented you the objectives of this project. So today I'm able to give you an update and show you some of the results that we obtained. And another project working on this aspect is also the fault scans project, which is still ongoing, and Florent, Aurélien, and Laura are still on the field in California to acquire data for this project. So I guess I can go very, very quickly on the introduction. You all know that under certain conditions that are never met, you can cross-correlate noise as two stations, and then you are supposed to retrieve the green function of the medium between these two stations. You all know that, and you also know that once you have this green function, you can use them as if they were actual seismograms to do some passive imaging or monitoring. And you have seen these figures several times already this week. And so, yeah, let's come back to this green function, because probably you remember Pierre saying that in theory, we should get all the green function, not only the surface waves that we usually see in the correlations, but also the body waves. And Alexandre also mentioned that these body waves are very important, very useful, and we would like to be able to use them to see deep structures in the subsurface. But as mentioned by Pierre, these body waves are also very difficult to retrieve in the cross correlations. Usually cross correlations are dominated by surface waves, and probably the main reason for that is that our noise sources are mostly located at the surface of the Earth, so they excite mostly surface waves. And so in the first time, what you see is mostly surface waves. So retrieving body waves is important but difficult, but could be interesting because they usually have a higher frequency content, so you could expect higher resolution imaging using them, and they are sensitive at depth, which, as Alexandre shows, enables to image and monitor faults, for example, at depth. But to do this kind of things, you need to see the body waves, to extract the body waves in the correlations. And one way to do that is to wait for a very long time and correlate very long time series, as Pierre showed. But not everybody has this very long time series, huge amount of seismic data to correlate. And so another way is also to look for stable and powerful sources of this high frequency body wave. So that's the direction we are going to here. And it turns out that trains are actually very good sources of high frequency body waves. We are not the first to see this. It was already noticed by Nakata, for example, in Oklahoma, I think, by Kiros and others as well, who already performed some body and surface wave imaging using train signals. Yeah, here what I show is an example that we obtained in the Pacific project by Phil Dales and others. I will probably detail the experiment a bit later. But what you see here very clearly is that with this particular dataset, if you correlate either everything or only quiet periods, as you would do if you try to get rid of some local sources, intermittent sources, then you get a cross correlation that is dominated by surface waves as very often. But if you focus on the time periods where trains are passing nearby, and you only correlate these time periods, then you reconstruct much clearer body waves in your correlations. So this is an example I will come back later, but this is basically the main motivation for this work, the fact that if you focus at the signals that is emitted by trains, we are able to retrieve much better the body waves in the correlations. And hopefully we can use them for imaging and monitoring. And so the imaging part is mostly done in the Pacific project, while the FoldScan project is focusing on monitoring. And today I will probably focus on Pacific because I won't have time to detail what is done in the FoldScan project, but Pierre told you already a little bit about this. And for doing so, we cannot work as usual, and we cannot really apply the standard ambient noise correlation workflow, correlate everything blindly, stack, and then try to do something with that. It really, and I will show you also that it really requires a very fine-tuned and dedicated workflow to work with these train signals. So this is something that I will detail as well. But first, we would like to understand the train signals. It's very important to understand the source of the signal and the source mechanisms. And that was actually my particular work within the project. So first, we can look at the train signals that were observed already by others. For example, Lee and others, Fuchs et al. And what you see is that these signals are very particular. They are very specific characteristic, especially when you look at spectrograms. And in particular, they have these very peculiar spectral lines in the spectrograms that are either flat if the train goes at a constant speed, but they may also ondulate like this. And we will see later that this means that the speed of your train is actually varying with time. So it has already been observed and used. It was partly understood already when we started this work, especially by Florian Fuchs, who was here last time in Cargès, but not completely. And so we really wanted to understand these signals in more details. So this is where I came into play. And when I started this, I started by reading. And by reading literature in another community, in the engineering community, where there are many people working on trains, mostly to reduce the noise because it's nuisance. While as seismologists, we are happy that trains generate noise. And so you end up reading papers about this with very sophisticated modeling that takes all the interaction between the train, the rail, the sleepers. Sleepers is an important component here that links the two rails and couples them to the ground. And finally, the ground, which itself has a structure and so on. And when you look at that, well, my first reflex was, wow, I'm not sure I really want to do that. And because it's not really my expertise, I don't have the tools to do that. And also, do we really need to do that for seismology? So in the first time, what I did is not this. I tried to extract what I thought was important for me, and also what I knew how to do. And what I know is how to inject a force into the ground. And in seismology, we have numerical software that does that simulate wave propagation emitted by a point force on the ground. So that I know how to do, and so I started with this, and I will show you that this is actually sufficient to explain most of our seismological observations. And I guess we are lucky that it is sufficient. So this, in the end, this is all what I will do in the following. I consider that the actual seismic sources are these sleepers So you have to imagine that there is the two rails on these slippers, but the force is really exerted on the slippers into the ground. And these slippers, these sources are excited each time a wheel of the train will hit them. So when the train passes, you will see the wheel hitting these slippers. And then what I just need to do, so yeah, this is the workflow, what I will simulate in the following. You have the rail track here. What you don't see is that it's actually, along this rail track, you have these discrete sleepers, but the spacing is very short. It's every 70 centimeters usually. And you have your trains that will travel along this railway with a given speed. And what I'm interested in is simulate the seismograms that I record here at some sensor when the train is passing. And for my simulation purposes, I actually use the source receiver reciprocity because I have several thousands of sources here, so I turn them into receivers just to reduce the computational costs. And what I need to do next is, for each of my slipper, each of my seismic source, I need to design a source time function that will represent the passage of the train as a function of time. And so as I told you in the first time, you can just consider that each wheel of the train hits the slipper when it passes, kind of instantaneously. And so quite naturally, you start by defining a Dirac comb to represent this. So here, remember, I am for a specific slipper. I'm not considering all slippers for the moment. But if you do that, it's actually not sufficient because what you will do is that you will overestimate the high frequencies in your spectrum. So you cannot really do that. It's not very realistic. What you need to do is to smooth this Dirac comb by something that accounts for the elasticity of the rail. And the consequence of this is that each slipper will actually see a wheel of the train before it arrives exactly at this slipper. And it will actually see several wheels probably at the same time. So in the end, you end up with this smoother time function that I need to differentiate just because I'm interested in computing ground velocities and not displacement. It might be a detail. It has also, of course, an effect on the spectrum, but it's not that important. So I end up with this source time function that represents the train passage over my slipper. And already the spectrum of this source time function tells me something about my signal, because here you clearly see the frequency peaks. That corresponds to the spectral lines I showed you in the spectrograms, and we will see that just after. And you also understand something about the mechanism in which train generates seismic waves. In particular, you understand that the characteristic length that is actually important is the wagon length. That is the true spatial period of your train. And then all the other distances between the pairs of wheels that don't introduce additional fundamental frequencies, they actually modulate the signal. So that's also something important to understand. And so once I have this source time function, what I can do is just inject it in my simulation. And these are the kind of seismograms I obtain at my sensor a little bit away from the railway, 300 meters away in this case. So on the left here, you have my numerical results. And on the right, you have observations made by Florian Fuchs on an Alperway station somewhere in Austria. And for two different type of trains. These are actually two different stations and probably two different trains as well. And what is interesting here is that what you observe on the right is two different signatures. Maybe it's not obvious at first sight, but here you have these very regular spectral lines with quite a narrow spacing, while here the spacing is a bit larger. And they are not exactly flat. If you look precisely, maybe you don't see it, but there is a Doppler effect here that you don't have here. So of course, my goal is to try and reproduce these observations. That would mean my modeling is somehow realistic. And so when I inject directly my source time function in my simulation, and this time assuming many sleepers along my railway, and of course when you do numerical simulation, the first thing you do is that you put regular sleepers. It's just simpler, and yeah. And if you do that with exactly regular sleepers, what you obtain is this signature, which is quite different from what you observe. So here you start to tell yourself, okay, I probably got something wrong, and it doesn't match. But what I got is this clear Doppler effect, which is a characteristic of a moving load along the railway. So when I saw that, I thought about it a little bit, and I started trying things. And what I did in particular is that I perturbed a little bit the location of my sleepers. So instead of considering exactly regular sleepers, consider slightly irregular sleepers, and then, kind of magically, I obtained this signature, which is very close to this one. So I was super happy about that. But coming back to this one, and I know this is a moving load because if I put only one wheel train on my regular sleepers, I obtain this. So this is clearly a moving load with nothing here. But this signature is still interesting because if now if you change the spacing between the sleepers, meaning if you change the characteristic length along the railway, if you make it longer, you could think, for example, okay, maybe it's not each sleeper that emits the waves, maybe it's just the ends of one rail segment. So that's typically of the order of tens of meters. Then you obtain this with spacing between the spectral lines that is shorter because your characteristic length is longer. Yes, I didn't mention that these fundamental frequencies, they're always of the form of train speed over some characteristic length, sorry. So here you have really two different mechanisms related to two different lengths. One is the wagon length, and this signature is really characteristic of a single sleeper seeing all the wheels of the trains, while this one is characteristic of a moving load, single wheel if you want, or single moving load moving over your railway. So two different mechanisms, two different signatures, and what is very interesting, I think, is that you retrieve these signatures in the observations. And so in the end, the modeling is really able to reproduce and explain the observations. Okay. And so that's just what happens when train speed is varying, you get this nice oscillation. And again, what is interesting is that you retrieve this in the data, and actually you retrieve the superposition of both mechanisms with a very narrow line spacing here at low frequency and the larger line spacing related to the second mechanism here. So yeah, I'll probably skip that. But no, the idea is that okay, we understand this train source time function very accurately now. How can we use this for passive seismic imaging and monitoring? In principle, we could use that everywhere where there are trains, and that's in a lot of places. And so let me focus now on what we did in the marathon test site within the Pacific project. So yes, the Pacific project, the idea was to use this for passive seismic imaging in a mineral exploration context. And we had this test site near the Lake Superior with this very nice array of almost 1,000 sensors and with a rail track all along. And so as I told you, the main source of noise here is actually the trains that pass along this rail track. And as mentioned by Pierre, they are very long, heavy freight trains, so they generate a lot of noise. And this is where we could make these observations that by selecting the time periods that correspond to the train passage, we recover the body waves much better than just considering quiet periods or considering all the records. So now I want to detail a little bit the dedicated workflow that has been developed by Laura Pinson during her PhD. She defended recently. So the first thing is to detect the trains, and here we're using the covariance method of Leonard Seydoux, which has been presented before. So just for detection. Once we have that, we actually beamform the noise data that we record in 1 minute windows around this time of detection. And so Laura does that minute by minute. And so minute by minute, you are able to track the train along the railway. You see here the spot here on the beamforming tells you the azimuth where the noise is coming. So it tells you that the train is here. Some minutes after, it's here. And now it's here in the south. And then what Laura does before correlating is to carefully select the pair of stations that are aligned with the train positions that she inferred from beamforming to perform the correlation. So first, selection of time windows, and second, selection of the pair station which, for these specific time windows, are aligned with the trains. So yeah, that's the same thing, just presented differently. And so when you do that, you can do that at low frequency, and you recover very nice surface waves that you are able to track along your array. And you can do that for body waves at higher frequencies, and then you see the emergence of this very nice body wave. I say very nice. Here you might say, okay, all this work for this, it's not super nice. You are selling this and we end up with this. But here it's actually a great improvement because this is for a single virtual source, while this was a stack for probably for all this fat line here. So this is not a local measurement. You cannot do imaging with this. While this is local for this specific virtual source, and you can do that for all your virtual sources in your array, and you can really use that for imaging. And so yeah, I'll skip this. So once you have your range function, of course, you can do some imaging either using surface waves or body waves, and this has been done by colleagues in Dublin. And very shortly, what I would like to do, I could conclude here and say, yeah, trains are great. They are powerful. They are repeatable sources of noise, and that's true, especially for high-frequency body waves. And that can be used for passive seismic imaging and monitoring. We understood the source signature in great detail now, so we really know what we are looking at. And it has a great interest for imaging applications because it provides a wide coverage. Of course, the coverage depends on the geometry of the railway or around the area of interest. But you need very few trains to get a very good SNR ratio and to see your body waves. You don't need to wait for years of seismic data. Initially, Laura was working with 6 to 10 trains, and in an area where you have many trains, with 60 trains, you have beautiful body waves. And for monitoring application, it means that you have a very high temporal resolution over potentially very long periods. And 1 year ago, I ended by saying, yeah, okay, the only drawback is that you need this very dedicated processing, so it takes a bit of time and effort, but it's really worth it. And I usually end it here. And today, if I have maybe 2 minutes, 1 minute. Well, actually, things are not that simple. And I remember Andrew, I think, asking me at EGU, okay, but your source time function is really harmonic. Is it not a problem for seismic interferometry? And at the time, I probably answer something like, no, it's fine, we correlate, and we are pretty confident we can use this for imaging. But we were really in the early stages of trying that. And since then, we have new data, new results. And so this is a dedicated experiment performed by our colleagues in Dublin, who actually showed, and I'll skip directly to what is interesting here, who showed that actually, yes, there is an imprint of the harmonicity of the train source time function in the final image that you recover, and very specifically, it's this reflector, for example. These, we know, don't exist in reality. It's an artificial reflector that is which has a time which is directly related to the frequency spacing in your spectrum. So yeah, the real conclusion is that there is still a little bit of work to do to get rid of this, and more theoretically, this is about the effect of correlated sources in the cross correlations, and yeah, people are working on this currently. Thank you very much.